take it away.
Sounds
Okay.
good. Thanks, Bill.
Go ahead.
So this is pretty exciting for me because normally I end up giving these sorts of talks to seismologists and explaining to them why geodesy is important. And this is maybe the opposite of my normal talk, where I don't think I'll have to convince anyone here why geodesy is important, but hopefully I'll be able to convince you that using it for earthquake response is important. So just a little bit of background about earthquakes and earthquake response for those of you who don't think about earthquakes 24/7. So as Bill mentioned, I work at the National Earthquake Information Center, or NEIC. It's part of the USGS located in Colorado. And we're responsible for locating and issuing rapid reports for global earthquakes bigger than magnitude 5, for West Coast earthquakes in the US bigger than magnitude 4, and for earthquakes in the rest of the US bigger than magnitude 3. So all in all, this means that we locate about 30,000 earthquakes every year, which is a ton. And most of these are small earthquakes. They're not felt. They don't have any significant impact on people. But on average, we expect about 16 major earthquakes every year. So that's comes out to roughly 15 earthquakes that are bigger than magnitude 7 and one that's bigger than magnitude 8. So if you've been paying attention to the news, you'll know that we've been sort of low on major earthquakes in the year 2022. We just had our first earthquake bigger than magnitude 7 in Japan just a few days ago. And last year, the biggest earthquake that occurred was a magnitude 8.2 off the coast of Alaska. And I'm going to use that as an example now to show you what happens at the NEIC after an earthquake. So we create these, what we call event pages on the USGS website. And it's made up of a bunch of different products that are given by each of these tiles. And I'm going to highlight a few of them that are going to be relevant to this talk. So the first one that comes out is this origin product. It's an estimate of the earthquake's location. So that is its hypocenter, which has a latitude, longitude, and depth. And it also estimates the start time of the earthquake. We also have the moment tensor, which describes the fault orientation, the direction of motion on the fault, which is known as the mechanism, and the earthquake magnitude. So there are a bunch of different flavors of moment tensor, and they all use different aspects of seismic observations to solve for the fault plane orientation. The W phase moment tensor is a long period moment tensor solution. And for large earthquakes, that W phase moment tensor is usually the first confirmation that we have of the earthquake's magnitude. And that's generally available from the NEIC within 20 minutes after earthquake origin. And if you're not familiar with moment tensors, this beach ball diagram that you're seeing here is not particularly important. Just know that it's what we use to estimate the orientation of the fault in space. Next up is the shake map. So this is a product that estimates the intensity of shaking throughout the affected region. And it uses both ground motion models to predict how shaking will attenuate as you move away from the earthquake source. And then it also makes use of seismic instrumentation in the near field and citizen science reporting of the intensity of felt shaking to validate and update those estimates. Next is the PAGER product, which stands for Prompt Assessment of Global Earthquakes for Response. And it's a rapid estimate of the human and economic toll of an earthquake. So this is an estimate that is affected by factors like the shaking intensity that we talked about just a moment ago, things like the population density in the area, and the seismic resilience of local structures. And it's on a scale from green to red, with green being low likelihood of economic loss or fatalities, and red being severe losses in one of those two categories. So ShakeMap and Pager are two of the most public-facing products, I would say, in that they don't require a lot of technical knowledge to understand what the products are telling you. But of course, they rely on some very technical modeling sort of behind the scenes to produce them. But because these products are useful not only to the public, but also our various partners in disaster response, they are produced as quickly as possible, so on the order of minutes to tens of minutes, and then updated as more information is gathered. So these take into consideration things like the origin, and then also instruments, data recorded on the ground. But the product that I'm going to focus on the most for this talk is the finite fault product, which is also known as a slip model. And it's basically an estimate of the location, the timing, and the amount of motion that occurs along the fault plane. So keep in mind that faults are not points. They're much better described as three-dimensional planes and, two-dimensional planes, and earthquakes don't happen, no, three, and earthquakes don't happen instantaneously. So really large earthquakes can take many minutes from the start to finish of motion on the fault. And then of course, that means that depending on where you're located, you might feel shaking for that amount of time or longer. And a kinematic finite fault model aims to describe the features of the rupture throughout the course of the earthquake. So this is the model on the event page that takes the longest to complete. And once it's finished, it gets fed back into those public-facing products like ShakeMap and Pager. So even though it's slow, it's important. And I'll give you a quick example of why and when the slip pattern matters. So here's two ShakeMap products from earthquakes in the last couple of years. On the left, this ShakeMap in Peru, you can see the earthquake's epicenters denoted by this orange star. And then the intensity of shaking in these images is such that warm colors indicates higher intensity of shaking. Cool colors is light to weak shaking. And on the left, this magnitude 6.5 earthquake, the ShakeMap is estimated in such a way that you can see that shaking seems to attenuate sort of evenly in all directions. It looks like kind of concentric circles of color. But when you get to these larger earthquakes, like this magnitude 7.3 strike slip earthquake on the right, you get this different pattern where slip is elongated along the direction of the earthquake strike. And that's because, as we mentioned, large earthquakes are occurring over some area of fault. And for these big ones, that can be tens to hundreds of kilometers in length. So a simple point source or a single rectangular patch, unlike the example in Peru that was shown here on the left, that's sort of insufficient for understanding a large earthquake's impact. So knowing the slip distribution, or at least the dimensions of slip, where slip is occurring, is crucial for those shaking predictions like you see here in ShakeMap, and then going further into loss estimates, damage estimates, and perhaps even tsunami generation estimates. So how do we get a finite fault model? So modeling requires that we prescribe the fault plane in advance. So we need to know the orientation, that's the strike, dip, and rake. And generally we get that from the moment tensor estimate that I mentioned earlier. And in this figure on the right, you'll see a map view of the orientation. And just to orient you, since this is this type of plot that I'll be showing throughout this talk, this red line at the bottom of the fault represents the up dip side. So that's the shallow part of the fault. And then even though it's in map view, you have to imagine this fault dipping at some angle down into the page, going underneath the Aleutians, which is the peninsula you're seeing here. So once we have this rectangular fault dimensions, we then divide it into smaller rectangular boxes that we call subfaults. So you can see each of those individual boxes in the image on the right. The star represents the earthquake's hypocenter, that's the initiation point of rupture. And then we invert whatever data we have available to find the timing and amount of slip on each of those subfaults that best fits our data. And then when we sum the contribution of each subfault, both the amplitude of slip and then its timing, that gives you the earthquake's source time function, or the moment release with time. And you can see the example from this Alaska earthquake on the left here. And basically this is just serves as a reminder that these ruptures can take a long period of time to complete. So in this case, the majority of rupture was over by about 60 seconds. And then we had small asperities toward the edges of the fault that continued out to nearly 100 seconds. So about a minute to a minute and a half of rupture on the fault. So NEIC has been producing these kinematic slip models in rapid response since late 2007, thanks to Gavin Hayes. And he also created this database of finite fault models dating back to 1990. You can see the relevant paper on the left. And these models were all produced with broadband teleseismic waveforms and produced in a systematic way so that they are easily compared one to another. And having a database of these finite fault models is important because these aren't just relevant for rapid response in the ways that I've mentioned before. They're also important for understanding just general characteristics of how earthquakes rupture and develop, because that means that we can use what we know about earthquakes of large magnitude to inform our models of future earthquakes, even before we have all the information. So for example, if we have a magnitude 7.5 earthquake, before we're able to finalize the finite fault model using this database, we already have an understanding of what a typical dimension of a magnitude 7.5 earthquake is, and that can be sort of used as a placeholder until we have information about this earthquake specifically. So this is what the NEIC has been doing now for 15 years, but there are some caveats for using this broadband teleseismic data. First, it requires really long data collection times. So in order for seismic surface waves to be observed, all the way across the globe, we basically wait about 45 minutes before we even grab the waveforms to include in the inversion to make sure that all of our stations have actually seen the earthquake. And because we're using data from stations at teleseismic distances, they're really only sufficient for earthquakes bigger than magnitude 7, where the amplitudes are big enough that they will still be included in data at that distance. So local data, and by that I don't mean just geodetic data, although I'll be highlighting that here. So it includes accelerometers, GNSS, and InSAR are becoming routine in our NEIC operations, which are now allowing us to model smaller earthquakes and more tectonically complex earthquakes. And I just want to give some quick kudos to my collaborators on this project, Pablo, Sebastian, and Diego, who have been working with me on this for the last nearly 2 years to get this part of NEIC's regular operations. And there's still a lot to do, but we've made a lot of progress. So for the remainder of this talk, I just want to highlight 3 examples of how geodesy has contributed to SLIP model results so far. I'm going to talk about the magnitude 7.2 earthquake in Haiti from this past summer, and then the magnitude 6.2 Petroleum, California earthquake from a few months ago, and then we'll go back in time even further to the 2019 7.1 Ridgecrest, California earthquake. So starting off with Haiti, so this earthquake will probably be familiar because it was a big news story. It occurred in August of this past summer and caused a lot of destruction, thousands dead, tens of thousands injured, hundreds of thousands structures damaged or destroyed, a huge economic toll. And for anyone who doesn't think about earthquakes on a regular basis, I just want to point out that this earthquake, because of the logarithmic magnitude scale, was actually nearly 2 times stronger in terms of energy release than the magnitude 7.0 earthquake in 2010. That was a huge news story for a very long time. And one of the major reasons that this larger earthquake caused less damage was just that it was in a less densely populated area further west of Port-au-Prince. So one of the complications with this earthquake is that there was an earthquake that occurred about half an hour earlier in Alaska that was a magnitude 6.9, and maybe an earthquake all the way in Alaska and half an hour earlier doesn't seem like a big deal, but when we're dealing with teleseismic observations and waiting for these signals to be captured at a global set of stations, an earthquake like a magnitude 6.9 in a small amount of time prior to this earthquake means that those signals are going to be tangled up in each other by the time we start looking at the Haiti earthquake, and make it more difficult to model. So basically what this meant was that a lot of the waveforms that we had from teleseismic stations ended up unusable because they had sort of these two signals together that we couldn't easily extricate from each other. So when building the finite fault model, here's a map of the region to get you oriented. So Haiti's on the left, Dominican Republic on the right. And this star represents the epicenter location of this earthquake. And here is the fault plain region. So again, red indicates the updip edge, and that's located here along the Enrico Plantain Garden Fault Zone, which is this kind of thick black line that you see. And then it's dipping into the page toward the north. So, back in the summer, this introduction of regional data was being done sort of ad hoc. So we started with just our teleseismic data sets. And this is the model that we get with the usable teleseismic waveforms that we had for this earthquake. You can see there's one main asperity very close to the hypocenter, and then 2 other asperities in either direction. And just to orient you, the difference between these 2 images, on the right-hand side, I've just rotated the fault so that you're looking directly at the fault. So the updip edge is now to the top. So you have to kind of rotate your head to get from map view into this view on the right. So this is all well and good. I was actually pretty happy with this model, despite having fewer observations than normal. It fit the data pretty well. And then we started getting information that suggested that shaking was significantly larger in amplitude toward the west of this fault than for the east, which suggests that there was likely some pretty strong directivity of rupture toward the west. And that's not really captured in this teleseismic model. but there wasn't a ton we could do with the data that we had. So it took us a while to get access to other data in the region, but eventually we were able to get static offsets from a handful of GNSS stations, waveform data from one strong motion accelerometer site in Port-au-Prince, and also 2 different InSAR interferograms. So obviously this was not a rapid model. This took us many weeks to put together, but this is the result of that joint model that includes not only the usable teleseismic data, but that accelerometer station that you can see here in the white triangle, and also these 5 static GNSS sites, and InSAR, which I'll show you in a second. And these static GNSS fits don't look fantastic, but just keep in mind how incredibly small this scale is here. So using all of this data, we get a very different picture of what rupture looks like. Indeed, we see this very directional sense of rupture toward the west. And we were able to get this result really thanks to the InSAR data in the region. And at the time, we didn't have InSAR capabilities included. So I just want to give another shout out to Pablo Koch, who worked very quickly on this, and also Bill Barnhart, who helped us understand InSAR data a bit better. So this is just one interferogram's result, but it's the more interesting one, I think. So in the top left, you can see the observed line of sight displacements, which we've downsampled to many individual points. And what's interesting about this interferogram in particular is that there's a pretty severe atmospheric ramp. And what I mean by that is if you look at the observed line of sight displacements in on the top left, you can see that there appears to be significant displacement even far away from the earthquake and outside of the, outside of the black box that denotes the fault area. And that's not physical. There's not actually deformation happening. It's a difference in the atmospheric conditions between the 2 acquisitions of that make up the interferogram. So we implemented not only InSAR capabilities, but also this sort of simultaneous inversion for the atmospheric ramp as well. So you can see that here. So this now gets removed from the deformation signal, leaving what you see on the bottom left here. So this is the our inferred deformation signal. So the whole line of sight signal minus the ramp, and then the synthetic line of sight in the middle here. And I just want to bring back this map just to clarify again how significant including this geodetic signal from the InSAR was to clarifying the directionality of rupture, and the fact that this earthquake in Haiti did not rupture in both directions along strike like I originally thought with my first posted model, but was actually pretty unilateral to the west. And so the caveat here is that, InSAR will probably never be available in real time unless we get incredibly lucky and our second InSAR acquisition comes, mere minutes after the earthquake happens. But despite that, I'm really pleased to say that this new capability has allowed us to model not only earthquakes like this one, where the teleseismic data was not of great quality, but also of other earthquakes that we likely wouldn't have even attempted to model before this year. So I won't be showing it today, but there was a magnitude 6.6 earthquake in China in January of this year. And as you'll recall, teleseismic data is usually insufficient for modeling earthquakes below magnitude 7. But because it was a shallow crestal earthquake, we were able to include InSAR interferograms that were collected over the next few days and publish a model of this magnitude 6.6 earthquake to our event pages and provide a level of detail about that rupture that we wouldn't have been able to in the past. So feel free to go look up that January earthquake in our event pages to see what that model looked like. So moving on to the next example, that's going to be the December 2021 Petroleum, California sequence. So this earthquake sequence occurred near the Mendocino Triple Junction. So that's a region that connects 3 different tectonic plates and joins the San Andreas Fault and the Cascadia Subduction Zone. So 2 of the most carefully watched tectonic boundaries of relevance to the United States. So this is a pretty seismically active region. So I just want to clarify that an earthquake in this area does not necessarily portend something significant to happen on one of those 2 other boundaries. But originally, this earthquake was interpreted as a single magnitude 6.2 event. And soon after, we realized that the data was not really consistent with that. So NEIC, working with the Northern California Regional Seismic Network, was able to identify this as 2 distinct earthquakes, one offshore and one just onshore. And the estimate is that the offshore earthquake was a magnitude 5.7, followed closely after by a magnitude 6.2. And because of their spatiotemporal proximity, observations that we have of either of these earthquakes, includes really the combined signal of both events, which makes it hard to tease apart. And on top of that, it's when you have 2 earthquakes that occur close in time, it's generally simple to locate the first earthquake in the sequence, but the second one is a little bit more tricky because it's sort of hidden in the signal of the first earthquake. So identifying, the details of this sequence becomes complicated. And despite having only pretty small amplitude signals in the GNSS data on land, because these were 2 fairly moderate earthquakes, not really big ones. Jerry Spark was able to estimate these GNSS offsets that I'll show you here in this map on the right. We realized early on that an earthquake in just this offshore location where we originally thought the earthquake was could not fit this pattern of deformation that we saw in the GNSS stations. I didn't include error ellipses on the arrows here representing the GNSS offsets, on the map. But the pattern of directional motion really could not be fit with just one of these earthquakes. And that helps to sort of clarify where these earthquakes were. So in this map on the right, black arrows represent the observed GNSS that Jerry estimated. Pink arrows are the offsets that we estimated from slip on the offshore fault. So that's this earthquake right here. Purple arrows represent offsets related to the earthquake onshore, represented by this purple star here. And then red is their sum. And really, we couldn't get the pattern of motion until we put point sources in each of these 2 locations, which confirms the event locations, which is especially helpful when you have a complicated sequence like this and it's hard to locate, especially that second event. So we've now taken this one step further and inverted strong motion accelerometer data in the area at the locations of the white triangles in this map on the right, as well as the static GNSS offsets, and have been able to sort of understand more details about, where and when and how big these two earthquakes in this sequence are. And of particular interest to me is the fact that these earthquakes actually appear to overlap in time. So if you look at the moment rate function toward the bottom of the page, you'll see that the second event starts about 11 seconds after the first, but that first event appears to still be ongoing. So this is work that's being led by Will Yeck at the NEIC. So hopefully that will be more available soon. But just to summarize this Petroleum earthquake, I just want to highlight how important these very tiny GNSS offsets have been to our understanding of this sequence. So picking and repicking that second event to try to locate is very difficult when there's signal from another earthquake involved. So these GNSS offsets were absolutely critical to confirming the locations of these two events, their relative sizes, and then finally to be able to estimate these in detail. Again, this is a model that we produced, in the weeks after this earthquake. This was not part of like typical rapid response that you see on our event pages. So I'm going to highlight that next in our final example. So can these new geodetic capabilities actually improve model timeliness and contribute to earthquake rapid response? So what timescales do we expect to have these two geodetic data sources, the InSAR and the GNSS? So InSAR, I mentioned earlier, if we get incredibly lucky, we might have a second acquisition in the minutes to hours after an earthquake, but I think that's never something that we can rely on. So let's just say that InSAR is available days after the fact. But GNSS is a little more complicated. The best estimates are available many days later, but real-time GNSS has been really improved recently so that it can be sort of incorporated into real-time estimates of the rupture process. But for anyone in here who's a geodesist but doesn't work with GNSS, I just want to highlight why real-time GNSS processing is difficult and how this may impact our ability to include GNSS data in rapid response products. So GNSS is basically a measurement of time of flight of a radio signal between multiple satellites and a ground-based receiver antenna. And that requires us to have knowledge of transmission delays of that signal through the atmosphere, and especially through the troposphere and ionosphere. But the conditions in the atmosphere are constantly changing and are difficult to know in real time. It also requires that we have precise constraints on the satellite orbits and clocks. So basically the time and location that the signal was sent from the satellite. But these both drift with time, and although we can estimate them with detail after the fact, in real time, they're also not very well known. And then, of course, we use the data of these time of flights from many different satellites in a complex least squares problem to determine our receiver location, epoch by epoch. But because of these constantly changing atmospheric conditions and the drifts in satellite clocks and orbits, real-time GNSS displacements are inherently lower in accuracy than post-process displacements that we can get, days and weeks later. So it's important that we understand how real-time GNSS data will affect our products, and whether it's actually even good enough to include in our rapid response products. So with that, I'll bring in the example of the July 2019 magnitude 7.1 Ridgecrest, California earthquake. So this sequence was the first major sequence for which we have truly real-time GNSS data. So before this, we had GNSS data that was processed after the fact using the satellite clock and orbits that were available in real time to sort of simulate real-time conditions. But this event was telemetered and processed in real time. So it gives us sort of a great example of what to expect from real-time GNSS streams. So just a quick primer on the tectonic setting of the Ridgecrest event. So the main tectonic boundary in California is, of course, the San Andreas Fault, shown in blue in this map, trending from the northwest to the southeast. And there's sort of this history of the San Andreas Fault transferring motion toward the east over time into these complex regions known as the Eastern California Shear Zone in green and the Walker Lane in brown. So these now accommodate about a quarter of the total tectonic motion between the Pacific and North American plates. So these are really complex regions where fault orientation is quite poorly constrained. If we have an earthquake that's located directly on the San Andreas, we can infer the earthquake orientation from our knowledge of the San Andreas Fault, but there are many complex orientations in the Eastern California Shear Zone and Walker Lane because of all of these complex tectonics at play here. So the Ridgecrest earthquake was located just north of this left lateral Garlock fault. So you can see we've zoomed in on this area here in red. And the magnitude 7.1 main shock in this sequence occurred on multiple northwest trending faults that you can see highlighted here in this bright blue. And they were also observed by dense strong motion and GNSS networks. So in this map, strong motion stations in the area are shown in black and GNSS stations in gray. Just the beauty of earthquakes in California is they're always very well instrumented. But of course, understanding these complicated fault orientations was only available after we had field surveys and InSAR observations that were able to provide detailed surface traces on which to model fault slip. And we don't have that in real time. What we do have in real time is the W phase centroid moment tensor that I mentioned before that gives us an estimate of the orientation. So here's what that looks like. This is the beach ball diagram. On the left is the moment tensor itself. And then now this straight line is sort of our planar estimate of the orientation of this fault. So it strikes from northwest to southeast, and it's nearly vertical in dip, so going straight down into your page. And I just want to mention that unless a region has a very well documented historical seismicity, originally we'll estimate the finite fault on both nodal planes. So that would be not just this northwest trending one, but also this opposite line in the beach ball diagram. So trending sort of perpendicular to this, but in this case, we know that this is the fault that ruptured. So that's the one that we're going to focus on. So in the next slide, I'm going to show you what real-time GNSS data from this earthquake looked like. And we'll focus on two stations in particular, station CCCC located here and station P595 located here. So both very close to the fault, I think within 25 kilometers for both of them. All right. And so here's what that data looks like. So in yellow here, I have waveforms in east, north, and up for both of these two stations. And this is, yellow is post-processed data. So this is sort of the best of the best, weeks later when we've better understood the atmospheric conditions and had better constraints on the satellite clock and orbit drifts, this is what we get. And then in pink and blue, we actually have two different real-time data streams. The pink one was processed by Central Washington University and blue by UNAVCO. And these are both real-time data streams using two different methods and plotted right on top so you can see how they compare to the post-processed, best of the best solution. And obviously there are some differences, but especially given the typical noise level of GNSS, these are really impressive in how similar they are. And a couple quantities that are important. One is the co-seismic offset that you can see shown in this example for station CCCC in the north direction. So this station has permanently moved about 20 centimeters to the north, estimated almost perfectly by the UNAVCO's real-time stream and slightly underestimated by Central Washington University's stream. And then another important metric from real-time GNSS data is the peak ground displacement. So if you take the sum of the component of all three components of motion and take the maximum amplitude of displacement, and that's important because we can use that in a rapid response setting to estimate the earthquake's magnitude. And that's what I'm showing in this image here on the right. So this is a graph of peak ground displacement on the y-axis, so that maximum displacement in the GNSS, plotted against hypocentral distance, so how far the station is from the hypocenter. And each station has its own, it is plotted separately, and then we solve for the best fitting line here that represents the magnitude. So these thick lines represent magnitude intervals of a full magnitude unit, and then these thinner lines are 1/10 of a unit. So the colors are the same here. Post-processed estimates of peak ground displacement are in yellow. Peak ground displacement estimates from Central Washington University's real-time stream are in pink, and UNAVCO's are in blue. And they track each other very well. And everything that's plotted in gray here is considered sort of below the GNSS noise floor, so it's not included. And then these lines represent our estimate of the magnitude when we take information from all the available stations. And all three of them estimate this earthquake to be a magnitude 7.1, which is a great first indication that real-time GNSS data is going to be sufficient for rapid response. But what happens when we want to use these waveforms that obviously have some differences in our finite fault models? So I'm just going to jump ahead to results from finite fault models for the Ridgecrest event. And these include both the accelerometer data from the stations that you saw on the map and the GNSS. Here's our finite fault model using strong motion and post-processed GNSS. And then in the middle is strong motion and UNAVCO's real-time GNSS. And then finally, strong motion and Central Washington University's real-time GNSS. So to orient you, we're looking directly onto the fault plane. So the left side of your page is the southeast direction, and the right side of your page is the northwest direction. And you'll see that the slit patterns here are incredibly similar. And another thing that you'll notice is the dashed rectangle that's included on top of each of these slit models. And that's something that we call the shake map polygon. And it's basically an estimate of the dimensions that best describe the ruptured area. And that's what gets fed into our shake map product once we have a finite fault model to update with the fault dimensions and get a better understanding of how the intensity of shaking looks as in the area affected. And you'll see that we estimate this shake map polygon based on the cumulative slip in the along strike and along dip directions. So those are those secondary graphs that you see to the top and to the left of each of these finite fault models. And the main takeaway here is that not only do we want our actual slip models to be similar between post-processed GNSS data models and real-time models, but we also want the dimensions and locations of this shake map polygon to be similar, because if we were to use real-time GNSS data to create a rapid finite fault model, we also want to know that our downstream products that take information from finite fault are going to be actually benefited by this model, and that the degraded real-time GNSS does not degrade our downstream products. So taking these shake map polygon rectangles and putting them into shake map, these are the results on the left of our model that used post-processed GNSS data, and in the middle, the one that used UNAVCO's real-time GNSS, and on the right, the one that used Central Washington's real-time GNSS. And they're all incredibly similar. So that's the main takeaway. There are inconsistencies, but they're barely noticeable when you look at the shake map product as a whole. But of course, I won't make you do that. I'll show you the details. So to clarify the differences, this is the MMI percent change. It's the modified Mercalli intensity, basically the intensity of felt shaking between the result that used the post-processed GNSS data and that with UNAVCO's real-time GNSS data on the left and Central Washington's real-time GNSS data on the right. So obviously there's sort of this low amplitude bias, actually in opposite directions across the whole area, but it's very low in amplitude. And you can also see some slight differences at the fault edges. For example, this little red patch here is where the dimensions of the shake map polygon were slightly different in that location. And then you also see these sort of weird looking half circles of higher MMI percent change. And those are likely due to changes in slope and uncertainty of ground motion to intensity conversion equations when you get to lower intensity shaking. So the intensities in those locations are already low, so these differences are not really significant from a rapid response standpoint. So all in all, these results and the small values of these MMI percent change plots suggest that using real-time GNSS in standard operations will not significantly degrade the quality of downstream products, although I will stress that all products can and perhaps should still be updated when we get better quality data. But this means that we have the potential to create these estimates faster when we include real-time GNSS data. So that's the last of my examples. So with that, I'll wrap up with some takeaways, basically from each example that we talked about. So from Haiti, we learned that geodetic data can help us to understand the rupture process when traditional seismic data is poor or unusable, in that case, because of that earlier event that was intertwined in the data. And then from Petroleum, that complex ruptures can be clarified by incorporating local data. And in this case, that GNSS helps to identify the rupture asperity locations, even for these smaller magnitude earthquakes. And finally, that real-time GNSS data appears to be sufficient for rapid slip modeling and does not sufficiently degrade downstream response products, despite the fact that real-time GNSS streams will sort of always be of poorer quality than those that are available days and weeks later. So with that, I'll wrap up. My contact info is on the bottom of the page if anyone has any questions after the fact, but I'm also happy to take questions now.
All right, thank you, Dara. I'm going to open it up for questions. First, I'm going to turn off the recording so that